Mr. True. In this video, I want to continue doing more examples of finding sector areas in circles. In the previous video where I introduced sector area and segment area, when I got to these problems of finding segment area, I did a very long process of finding sector area, and it was long because, well, I wanted to review some knowledge that we learned in the previous videos and in our class of working with isosceles triangles, dropping down altitudes, and I just used the basic formula of finding an area of a triangle, which is 1/2 the base times the height. Now I'm not going to highlight the height in this triangle because what I'm doing in these two videos is use some areas of triangles that, depending on what class you're in, you might have seen these in pre-calculus and use them quite a bit if that's why you're watching this video and you just have a question about some random circle problems. If you're in a geometry class, your geometry book should have by now introduced a couple of various ways of finding areas in triangles. And it's not just area is equal to 1/2 base times height, because as you saw in my video introducing sector area, while that was a lot of good review in finishing that problem, it was long and cumbersome. So we have two more convenient ways of finding areas of triangle. We have the area of a triangle when you know two sides and an included angle. That means you know two sides of a triangle and the angle that's in between those. Well, the area of that triangle is going to be found more easily by simply doing 1/2 of A times B. Now the lowercase letters in my textbooks are the sides. So these would be like my two sides of my triangle, and times the sine of C. Now that's going to be the included angle. So in words, it would be actually easier to say that the area of a triangle is equal to 1/2 multiplied by the two sides of the given triangle that you know times the sine of the included angle, the angle that these two sides help to make. So the area of this triangle would be 1/2 times 4 times 7 times the sine of 27, and just make sure your calculator's in degree mode, and there's your answer. That saves me for questions like this, like I did in the previous video, going through all of the work of finding not only the height of the triangle, but the base, because in this triangle I don't know either one. Now another way of finding the area of a triangle, which we're going to do in this, you're going to use this on the second example of my two example video here, is something called Heron's formula. I should have wrote it up here, H-E-R-O-N, Heron's, well, apostrophe S, Heron's formula. The area of a triangle when you know the three sides of the triangle. You don't know any of the angles, and again, of course, you don't know the height, because then you could just do area is equal to 1/2 base times height. The first thing you're going to do is find this variable called S. Now with Heron's formula, S is equal to 1/2 the perimeter. So you would take these three sides, add them up, and divide by 2. Once you know what S is equal to, half the perimeter, the area formula, these go together, you have to do both. The area formula is equal to the square root of S times S minus A times S minus B times S minus C. And again, these two formulas are very nice because they really speed up the process of finding the area of a triangle if you're not given, you know, some of the nicest information. So let's see what it looks like here. I have a circle with a radius of 7, and I've got this arc out here of 260 degrees, and I want to find the area of the segment. Now, all area problems in geometry, pretty much, I'm sure there's some example we can come up with, but pretty much all your area problems where you have like a bunch of shapes together and just a portion is shaded is always going to be the same. Find the area of the large region and subtract out the area of the smaller region that is not shaded in. So we're going to find we're going to find the area of the sector right here, and to find the area of a sector, that's going to be sector area is the measure of your arc. In this case, it's going to be arc AB over 360. And again, all that is part over whole. It's just what percent of the circle do you want to find the area of. So it's the measure of the arc over 360 times, and I said what percent of the area of the circle do you want. So it's, you know, what percent of pi r squared minus the area of the triangle. Well, now here where I'm going to skip all that work I did in my previous introductory video, I want to find the area of this triangle. Well, one side is 7. The other side is 7 because these are both radiuses or radii of the circle, and this angle inside that's included between these two angles, well, 360 degrees is what, you know, you rotate inside a circle, and 260 are already taken up. So 360 minus 260 is 100. So let me write the formula out. We just got, 1/2 A, B, sine of C. And, this could also be 1/2 B, C, sine of A. Whatever two lowercase letters are here, the other letter is at the end of that formula. Your textbook might have given you 3 versions of that formula. Well, let's plug in the numbers, and I will need to refer to my notes because this is going to come out of the calculator. We have our the part of our triangle that we're concerned with is the 100 degrees out of the 360. Times, and I don't think I did any of this in exact form. No, I didn't. So it's going to be 100 divided by 360 divided by, times 3.14 times our radius, which is 7 squared, minus 1/2 our included, our sides that include the angle. They're both 7. I could write 7 squared, but keeping it exactly how that formula is written, times the sine of 100. And that's it. You kind of make you wonder why I did such a long example in the previous video, but I reviewed 60-30 triangles and finding heights and bases and all kinds of good stuff, altitudes of an isosceles triangle, bisect the vertex and the opposite sides, a perpendicular bisector, blah, blah, blah. But if we just want the answer, 100 divided by 360 is 0.278. We got 3.14, of course, times 49. Minus, I showed more steps here than I kind of expected I would have. 1/2, whoops, 0.5 times 7 times 7 times the sine of 100 comes out to be 24.13. This mess, when you get it typed into your calculator, if you have a 2-line scientific calculator or a calculator where it's very, very easy to enter fractions, really, honestly, I would just type all this in at once and get the answer just like that. I'm just showing you some steps, though, if you need it. 42.77 minus 24.13. And that comes out to 18.64. Now, don't forget you're finding area, not length, so it's 18.64 units squared. Last example. Here we have a triangle with a radius of 5 and a chord length of 9. A chord is a segment in a circle whose endpoints are on the circle itself. And again, this is going to be an isosceles triangle because, well, these are both radiuses and their lengths, therefore, are going to be equal. And I want to find the area of this segment. Well, we're going to, if this side is 5 and this side is 9, we of course automatically therefore know the opposite side is 5, and we have a triangle where we know all 3 sides. So, the measure of our arc. We got a little bit of a problem here, don't we? Okay, now as far as the measure of the arc goes, we still need to do a little bit of scratch work. Now there's a couple of ways to find the measure of this arc, and I'm looking for this angle, we're going to call this theta, right here. We can do law of cosine if you know that. The law of cosine is that a side squared is equal to the other 2 sides squared and added together minus 2 times those 2 sides times the cosine of theta. But my students have not learned the law of cosine yet, so I'm not going to use that. What I'm going to do is I'm going to pull this triangle out, and I'm only going to pull half of it out because at this point, except for these couple of these fancy formulas, and I haven't really derived how these come about because we haven't talked about law of sine or cosine in my geometry class like I have in my pre-calc class. And just going to look at the right triangle here. And again, I still need to pull in some math skills that I used in my previous video, like I said, where I did that long-winded example. This is an isosceles triangle, and when you drop an altitude in an isosceles triangle, it becomes an angle bisector of the vertex, and it bisects the base. So this 9 is going to get bisected or cut in half, and this is going to be 4.5. Of course, we know this side here of our isosceles triangle, which is now going to become the how could I forget this? The hypotenuse is equal to 5, and we're going to find h, which is actually, I don't need to find that. Excuse me, I'm not using the old method. I want to find out what this angle is up here. And I'm going to, again, let's just call this capital A. So I want to find the measure of capital A, angle A. Well, from angle A, I know the opposite side and I know the hypotenuse. So if you remember, SOHCAHTOA, sine is opposite over hypotenuse. Cosine is adjacent. So cosine is adjacent over hypotenuse, and TOA, tangent of an angle, is equal to the opposite side over the adjacent. Well, I have the opposite and I have the hypotenuse, so I'm going to be using sine. So the sine of A is equal to opposite over hypotenuse. And of course, this is going to come out of our calculator, so refer to my notes. 4.5 divided by 5 is going to be 0.9. We're going to get the sine function away from the angle by doing the inverse sine function. And the inverse sine function, remember, with a regular trig function, you put in the angle measure and you get out from the trig function the sides of the triangle. Well, with an inverse trig function, this 0.9 is, of course, as you just saw me do, the ratio of the sides, and you get out an angle measure. The inverse sine of 0.9 is approximately 64.16. Okay, now that means that in my drawing here, theta is not equal to 64.16. Remember, I cut this isosceles triangle in half with an altitude so I could, use some right triangle trigonometry. So that's only half the angle. Theta is two of those measurements. Theta is 2 times 64.16, so it's going to be 128.32. Let me just double check here. And 120. Excellent. Okay, now I can get back to this shorter way of doing this problem, and it is shorter, I promise you. So the measure of the arc, the central angle is 128.32 degrees, so therefore the arc is as well. Times 3.14 times the radius, which is 5 squared, minus, okay, Heron's formula. The triangle is 5 and 5 is 10, 10 and 9 is, of course, 19, and so S is equal to, let's do some more scratch work here, S is equal to 19, but, S is equal to 1/2 the perimeter. So S is equal to 1/2 of the overall perimeter of the triangle of 19, and that means that the answer is going to be, what, 9.5? So we have 9.5 times 9.5 minus A, just pick a side, 5, times 9.5 minus 5 again, because we have two 5s, and 9.5, I'm almost running out of room, 9. And when you get all that in your calculator correctly, we get 128.32 over 360 times pi times basically 25. That comes out to be 27.98. This comes out to be, if you type it in correctly, 9.81. And our sector area comes out to be 18.7 square units. So, hope this helps you with your homework and maybe some of the harder problems at the end of your assignment if you're just in geometry or maybe just any other regular random question in your math class. I'm Mr. Truth. Thank you for watching. Go do your homework.